Right. Yeah, so I guess now the pressure is on me to talk about smart stuff. Yeah, so I'm Jonas. This is, again, joint work with Maryam Garba, Tom Nye, and Stephan Huckemann, who also is my PhD supervisor. And I'm talking about the Wald space for phylogenetic trees, which Tom has already pointed to at the end of his talk. And let's dive right in. So first of all, I give, again, a quick recall, a motivation for tree spaces in the first place. Then I will construct the Wald space and also talk about the geometry, how it is constructed. And then finally, we will do some numerical computations in Wald space. So yeah, let's start. So I think Tom has already explained that very well. Phylogenetic trees are inferred from common genes, and usually different common genes result in different phylogenetic trees. So you will naturally obtain a sample of trees, as you can see here. So this is supposed to be a fish, a horse, and an elephant. So I use way less fancy graphics than Tom does. And you have these edge lengths here, these positive numbers. And so you need some kind of statistics to infer the true tree. So you would want to take an average, for example, of those trees. And for that, you need an underlying geometry of the sample space, right? And of course, first of all, the geometry should be biologically reasonable. Second of all, it would be great if it's computationally tractable, so we can actually compute something. And to this end, fix again small n to be the number of species that we consider within one tree. We will just use the symbols 1 to n. So for example, in these phylogenetic trees pictured here, the fish, the horse, and the elephant would be replaced with 1, 2, and 3, respectively. All right, so a quick wrap up. There are existing tree spaces. The most popular one is the BHV tree space. And yeah, again, as a quick recall, it takes the rooted phylogenetic trees with leaves 1 to n and root 0. And it's basically, as Tom already pointed out, essentially an embedding of all those phylogenetic trees into a very high dimensional Euclidean space. And then you take the induced Euclidean geometry on this stratified subset, and you will obtain a very nice metric space where you have the ability to compute geodesics in O(n) to the power 4. And it's Riemann stratified, which means that it's a union of Riemannian manifolds. They are all flat, of different dimensions, and they are glued together in a very particular way, so that these Riemannian metrics on those manifolds are compatible in some sense at the glued boundaries. All right, so as an example here, you could visualize the BHV space for 3 species. You can embed this into the R3, and it's basically just 3 rays glued together at the origin. And then you also do the Cartesian product with a positive 3-dimensional ortho in this case, which is just adding these pendant edges, so these edges that are connected to the leaves. And with this Cartesian product here, you don't change the geometry of the space at all. All right, so now let's consider an example why we are motivated to define maybe different phylogenetic tree space. It's a little different from Tom's example. So let's consider these 2 trees here, T1 and T2, in blue and red respectively, with positive edge lengths L and the same edge length on each edge. And now think of what happens when all these edge lengths go to infinity. So the information that these trees convey is basically all those species are not related to each other anymore. But in the limit, both trees basically convey the same information, namely exactly that those species are not related to each other anymore. So, all right, I have to point to the laptop. So basically, what you would want is that a metric defined on this space should go to 0 as L goes to infinity, right? Because in the limit, those objects are considered the same thing. And when you try to picture the limit point, well, what comes to the mind is this forest here, where you have basically 4 isolated vertices, all labeled respectively with 1, 2, 3, and then also the root would be isolated. So in some sense, the root doesn't make sense anymore. So we consider unrooted forests. And in this case of the BHV space, it's actually the case that this distance grows to infinity linearly as L goes to infinity. Okay, so that's why we want to construct a new space, or that's one of the reasons. Yeah, and let's do that. So we take, we define the Wald space, which is for now just a set. It's a set of all those forests with n taxa, roughly speaking. And then what we do is, given such a forest, you could define between taxa or species U and V in the forest, which are in the same connected component of the forest. You can define the distance between them by just adding up the edge lengths of all those edges on the unique path between those vertices U and V, right? Because each connected component is a graph theoretical tree, so you have a unique path between each of those vertices. Right, so we have this notion of distance between U and V, for U and V being connected. And now we define this strictly positive definite matrix, sigma f, for such a forest in the following way, namely, it's an n times n dimensional matrix, where each, the UV entry is just e to the power of minus the distance between them. This is the same formula, basically, which you saw on Tom's slides with this Lij. And also, if they are not connected, we just define it to be 0. And as a sanity check, if you would let duv go to infinity, then this expression would go to 0, which is just this number that we assign if they were actually disconnected. So this kind of makes sense in some way. And referring to the previous question, to prove that this is strictly positive definite, you make some very mild technical assumptions to the forests. And it's definitely not trivial to show that it's strictly positive definite. But it's very important for us that it is. All right. Now we define this map from F to this covariance matrix sigma F here. We define this just to be phi. And so we actually have an injective map from the Wald space, which is up to now just a set, into the strictly positive definite matrices. All right, so now the question is, how do we define a metric on this, for now just a set on the Wald space, Wn? Okay, for this I've made a small analogy. All of you know the two-dimensional sphere. You can just see it as a subset of R3. And then consciously, we choose the Euclidean geometry on R3. And what we do is we take the infinitesimally induced metric to obtain the spherical geometry on the sphere. Okay, so this is the arc length distance then on the sphere. This is a length space, metric space, a length space. So distance between 2 points then corresponds to the length of the shortest path between those 2 points. And this shortest path is on the sphere itself. It's not necessarily in R3. All right, then you just look at the sphere independently of this ambient space, this blue ambient space, and you just take this one as a metric space. And very analogously, we do the same thing with Wald space, basically. So we take the set of forests and add it via phi into the set of strictly positive definite matrices. And I have scribbled this weird looking set here because up to now we don't know what it looks like. So it's just phi of the Wald space, basically. And what we do is consciously, we choose the Fisher information geometry, which has many different names, also affine invariant metric, scaled Frobenius metric, Killing metric, or Fisher-Rao geometry I've also heard over the course of the conference. And then we take the infinitesimally induced metric to obtain the Wald space geometry on this subset, whatever that is, right? Whatever that turns out to be. And then we go back into our set of forests via this phi map, via this embedding to obtain a metric space. All right. So now we have the metric space Wn, although we don't know what it actually looks like at all right now. So, but there are some theoretical results already. Just as a quick remark, it contains the BHV space setwise. And here I have written n-1 because basically the root will be just seen as another taxon, as another species. So it's a subset of Wn, of the Wald space, but the geometry is completely different. So just set-wise, it is a subset. And now also furthermore, Wald space is connected, even though we let some edges go to infinity, that's all fine. And the distance between each two forests you can pick out of Wald space is actually finite with this infinitesimally induced metric. Also, Wald space is a stratified space. That means it's a union of manifolds glued together in a certain way. And very nicely, going back to our motivational example, we actually have that the distance between those two trees goes to 0 as L goes to infinity. And the limit point F here, it's actually the limit point. So this forest is actually the limit point. And it's part of our space now, which is very convenient. So we have this biologically desirable property in our space. Right. So that was so far all to the theoretical properties of the Wald space and how the geometry is defined. Now let's try to do some computations in Wald space. When I talk about computations in Wald space, we basically want to compute shortest paths. So geodesics in a metric space sense, of course, because it's just a metric space, it has a lot more properties, but it's a metric space. So we want to compute shortest paths in this space. Now, we want to use the embedding. So we want to use this ambient geometry of the whole set of strictly positive definite matrices that we have, because it's a very nice Riemannian manifold, analytically defined. And the first thing we do is we just identify the Wald space with its image, just for simplicity. So when I talk about matrices that are part of Wald space, it's the matrix corresponding to the forest in Wald space. Now, as I just said, the strictly positive definite matrices with this particular geometry is a very nice Riemannian manifold, and we can actually make use, and we will make use of the Riemannian exponential and the Riemannian logarithm of this manifold. I spared you the formulas. For this talk, magically, we assume that we have a projection pi from the strictly positive definite matrices onto Wald space, which is not trivial at all, but it's possible to do it numerically with some tricks. All right. Now what we do is, for now, assume we have already given a discrete path in Wald space. So we have 2 points, say P and Q in Wald space. We have already given a discrete path. So we do everything numerically here. So it's a discrete path with capital N points. Now the question is, can we make that path in some sense straighter or in the same sense shorter, such that it actually is a geodesic in the end in this metric space? And for that, we use a particular algorithm, namely the path straightening algorithm. And just to show you how it basically works, it works in the sense that we use the ambient geometry. So here you can see this very barely, I think. This is the Riemannian logarithm. So this is a vector from pi to pi minus 1. This is a vector from pi to pi plus 1. So this is just a zoomed in section of our given discrete path here. And we basically compute this vector xi by just adding those two vectors up in the tangent space of pi, dividing by 2. So we basically obtain the midpoint of the parallelogram spanned by these two vectors here. And then having this direction, which we are supposed to go to, we just go there via the Riemannian exponential in our ambient space, but this is not necessarily a point in the Wald space anymore. So what do? We just project back to the Wald space and we obtain an updated point pi prime. So this algorithm is supposed to basically straighten out the kinks in the path. All right. Right, and basically what we do is we update the points P2 to Pn minus 1 in this path, and the points P1, so P, and Pn, so Q, will be fixed throughout this iterative procedure. So we basically update our interior points of this path several times, and then we hopefully straighten the path. All right, so this is just the theoretical notation of this algorithm. We compute this vector x, we just add up those two vectors, divide by half, so we have this midpoint of this parallelogram. And then we actually make the step and go in the direction, obtain a point in the strictly positive definite matrices, which is not necessarily a point in Wald space anymore, but then we project back and we're safe to have a point in Wald space. All right. Now let's have an example. And the question for this algorithm is, where do we get our starting path from in the first place, right? So we could just take the BHV geodesic, right? Just use the nice algorithm that is computationally tractable. And this is exactly this cone path here, the red line that goes through the origin. And I should say, so T2 is a tree with that tree structure here, and T1 is a tree with this tree structure. And we just see a two-dimensional slice of the Wald space, because you have to see that here there are 7 edges in this tree. So it's basically a 7-dimensional object. But we just look at these interior edges, these two, so we actually have a 2-dimensional slice. Now, here's a third tree structure, which comes into play when we actually apply our path straightening algorithm. So we start with this BHV geodesic, where the geodesic is actually going through the cone point, and it actually diverges away from this cone path to some dark red path, which looks quite smooth, and somehow converges maybe to the other path here, to this blue path. And then the blue path is, so we took another starting path, computed via an algorithm which I don't show you today, which is supposed to give a good proposal for a first starting path. And we do only 60 iterations, and it kind of looks a little bit unchanged, but a little bit more smooth maybe. But from this picture, we cannot really assess the quality of the paths, right? It's just a visual, it's not isometric. So what could you do to assess the quality of a path? Well, you could just compute the energy of a path. And for those of you who don't know what the energy of a path is, all you need to know is basically the smaller the energy, the shorter the path, and also the more equidistant the points will be distributed along the path. That's what the square is supposed to do, basically, to make these points on the path equidistantly distributed. Now, looking at the energy, what we see is, first of all, the energy of the BHV geodesic. I just plotted this as a straight line for reasons of comparison. On the x-axis, you see the iterations of the path straightening algorithm, and this is just the energy of the BHV geodesic. It's compared to everything else, it's quite high. And then applying the path straightening algorithm, we actually decrease the energy quite a lot, and it decreases throughout all these 200 iterations, basically. And it tends to also decrease a little further if we would do more iterations. So that's a good sign, because energy decreasing means shorter path and more equidistant points on this path. So it seems to work. Now for the other starting path, so this is the SP algorithm, which I could not show you today because of time constraints. This is the starting energy of this output of the SP algorithm. Successive projection is the name. So this is just another starting path proposal. This has a lot less energy from the beginning onward. And then the path straightening algorithm actually also decreases the energy, and it's still a little lower than the BHV geodesic after 200 iterations. So it's a little bit a sanity check to use the BHV geodesic here and apply the path straightening, that the energy actually also converges in some sense to this energy level. All right, and as Tom has already addressed the question how to compute geodesics between different tree structures, it's basically based on this ambient geometry which we use and using the projection. And yeah, it's seemingly possible to do that. And with that, I conclude. And yeah, that's the Wald space.
Thank you. We have time for one question. Do you have a question on the Zoom session or here? Yes.
I have to choose between my several questions. Or...
Yes.
Okay.
Sorry.
Yes. So maybe my main question is: could you give more details about the projection, the projection from SPD to the Wald space?
Yeah. So it's based on a gradient descent, right? but you have to think of your space is basically divided in patches because it's a stratified space. So what you do is you start in a reasonable manifold, right? You have a union of manifolds. Your space is a union of manifolds that are glued together over various boundaries, which are themselves, again, lower dimensional manifolds. So you start in some reasonable manifold of the highest dimension, which are the fully resolved trees, basically the trees with the most possible number of edges. And you start in a reasonable such a manifold. And in this case, reasonable is, well, if you have a point in Wald space and you go with your Riemann exponential out of this point and you project back, what you would expect is that the tree structure doesn't really change if you go very small steps. So as a starting manifold, you would take the one with the same tree structure as in this algorithm as the point that you had before in Wald space, which had already one tree structure. So, but when crossing some boundaries, you have to basically look in each possible direction or in each possible attached manifold you could go to. But luckily, these are only linearly many. When you're going from a fully resolved tree to a specific boundary, or let's say to a boundary which is not a forest, which is disconnected, because then you could, if you have a forest which is disconnected, you could connect these connected components within this forest in many, many different ways again. But this doesn't happen numerically, and I suppose that the forest stratum is somehow a cone point which is avoided in some sense by the geometry. But usually what happens is you have a fully resolved tree, and edge length goes to 0, which you have seen in this two-dimensional slice. And then you could only have basically 2 more possible tree structures that you could go into. So basically 2 other manifolds you could go into. So you have a look at them, so you go a little bit and see if the gradient descent sends you right back. And then you go into another one and see if it sends you right back. And if it doesn't, then you continue to go.
Okay, thank you.
Okay, so you have one question on the Zoom chat. So from Alexander Soen, I am wondering if there is an extension to reasoning about more general trees, just when the leaves do not have to cover all labels, or perhaps when they are labels appearing multiple times in the leaves.
Okay, yeah. So for the second case, when you have a leaf labeled more than once, our map that maps the forest to a covariance matrix will actually map to a degenerate covariance matrix. So it's not invertible anymore, and you cannot apply the Fisher information geometry anymore. So we have naturally excluded those from our Wald space, which also kind of makes sense biologically because you're comparing different species, right? So you're thinking about you're kind of requiring that they're not appearing on the same vertex, which would mean that they're the same species. On the other hand, comparing trees or forests with different number of labels or species, I think that's people have tried this and done this, but I think it's quite hard to do actually, and I'm not sure whether this is doable here. What you could do, well, you get a covariance matrix of a different dimension, right? So if you have one species less, it will be just a covariance matrix of n-1 times n-1. So what you could do is you try something like compare your n-1 times n-1 covariance matrix with all possible sub matrices of, but yeah,
these would be standard methods to compare.
But we're not concerned with this. So yeah, but it's an interesting question nonetheless. It's very hard to do, I think.
Okay, so thank you very much. Move on to the